Alrighty then, good Thursday afternoon to all. Thursday, the first week of classes is always a great time because it's the weekend almost, close enough. Today I'd like to actually bring some geology into this concept of climate sensitivity, and we'll exercise the concepts we got on Monday by looking at 3 geologic examples. And basically for 3 geological examples, they're all global warming events, they're all associated with CO2 changes. And what we're gonna do, what basically the analysis for this assignment will be to take the temperature change and the CO2 change and try to estimate a sensitivity. And what we're gonna see is we'll get different estimates of sensitivity, and then we can start thinking about it. So in general, the first day of a module is going to be more or less what you did on the other day. Look up something, get some facts, get some information, maybe play with it a little bit. On the second day, we'll play with more information, a little bit deeper in depth. And then on the third day, we get more subjective about what does it mean. It's one thing to calculate something, it's another thing to say, okay, the significance of this is. So that's the skill set we're going to keep practicing today. We'll set up to do what I call the back calculation. I don't know if that's everybody else's turn or not. Before I get started, are there any questions or issues that anybody's come up with trying to interface with things? No questions yet. All right, let's see if we can move this thing along. I'll spend a little time reviewing the homework assignments. This session's homeworks are not fully evaluated yet, so just give us a little time and they'll get a little bit longer. I'll dig into the geologic examples of global warming, 3 different time slices, 3 different lengths of time, 3 different times in the geologic history. And we're going to see if the climate sensitivities are the same or not, and I've already given it away they're not. And so why might that be? But to do that, we're going to quantify it with a back calculation, and then we'll worry about, so what? What does that matter? Which is sort of a follow-up on the bonus question. Why would we even want to deal with that if I'm making this case that climate's not sensitive and this is a very linear relationship? We'll explore that a little further. It's a bonus one time, and then it becomes the homework the next time. All right. Generally, a couple of tidbits to guide us, and we do this to try to provide feedback to you because you're asking a fair bit of work, not massive at any one time, but it's our responsibility to give you some feedback on it. Sometimes things could have been improved in general on answers, not necessarily any specific one, if you gave ranges of temperature in CO2. Oftentimes the answers are a little bit on the brief side. Show you math, show you work. Sometimes if you just give me a number, I don't know where you got the number, if it's some kind of number generator or something that came off the internet or something you made up because it just sounded like a good number or something. So justify it a little bit. The answers, even if they're mathematically inclined, a couple formulas or a couple sentences that says, okay, I do this and this is why I'm making this division, really helps demonstrate that you have a good perception of what's going on there. And if you don't have a good perception of what's going on there, then we can help you, we can work on that. So try to give even if you're doing math, show it, and give a little more length to it. Third point's about the same. A lot of the things for the first day, because you're looking up a piece of information, how much detail do you really need? You said, what is the CO2 level for 1950? It's a number, parts per million, okay. As we go to more analysis from today and for the third day, then a little more depth is going to be useful. Also, we're going to be asking you as we look up information, let's go ahead and get in the habit of giving me the links or the references if you have it. Basically, they're going to be computer links, just so I can see that you in fact look them up. Anybody have any question on these comments? Your specific comments will come back to you. We will be making comments on the each question individually and then collectively sometimes if there's a pattern that we can see. All right, the past is behind us, let's move forward. Why are we doing this? First of all, the climate sensitivity by definition is supposedly a simple number that gives us some idea if we, as we change CO2, how much the temperature is going to change. And there's no exact basis for that. We've estimated that in a variety of means, and you're going to estimate it. There's all kinds of different ways to estimate it. It's useful as sort of a conversational point, though. In other words, if I want to talk to somebody about, you know, how much is increasing CO2 really doing? Is it 1/10 of a degree? Is it 5 degrees? I can bring in the example of doubling it gives you a 3 degrees Celsius temperature change. And I'd have to convert that to Fahrenheit for most folks, but that's fine. So it's a simple number. It's more of a tool, communication tool, than it is a scientific thing. I don't know of any experiment that's actually, there's a lot of experiments to calculate it. They'll do some fancy stuff to do the calculation, but I don't know too many people that are actually using it as, oh, now we've got that number, what do we do with there? It's far from perfect. The far from perfect part has the fact that the ranges are all over the map. They can be, 3 is the average, but there's things up almost 6, and 6-degree temperature change would be a very significant outcome after you double CO2 than 3 degrees temperature. On the other hand, there are many estimates that are in the 1.5 degree range. So we double CO2 and a 1.5 degree temperature change is less daunting than a 5 degree temperature change. The problem parts, and we've talked about uncertainty a little bit the other class, is because it's so range, how do you convey both that there's a dependency, but we don't know the exact answer? This is a conundrum with science in general, because we don't know exact answers. We know something. We know a lot of things. We know certain things. We know a lot of things better than other things, but there's always some guess to our estimates, and we call them estimates for a reason. And this one is, to me, personally troubling for the reason that we've never been able to pin it down. And then superimposed on that is a philosophical question, which you'll see again in this class, sort of down the road. If we really can't predict the future because it's a nonlinear system, then why am I even bothering with it? Well, I'm bothering with it because that estimate would be the conservative minimum. It could get a lot worse. I mean, we're in this mode of there's things are progressing and they may get worse and they may get worse, but it's potentially nasty that they could get worse a lot faster than we want. All right, so for now we want to dig into this as an example of how we've come up with estimates. There were several different techniques, including temperature changes from modern measurements. There were modeling outputs. There was the paleo line, which is the one we're getting into. And we're going to look at the geologic past to make a couple of estimates. So the rest of the lecture is more or less some of the geologic background to set you up. So far, so good? Okay. What the temperature rise, we did this in a simple case. Now, we go on to do the inverse of it. We want to figure out if so-and-so changed the CO2 this much, and we want to get into those. We want to look at these things because there is actually a range of global warming events. I mean, there's not many 20-degree Celsius warming events. There's an upper limit to how fast the atmosphere or how much the atmosphere can change. Depends on your time scale. If you want to wait 10, 20 million years, you can change it a lot. If you want to worry about 10 years, there's less change as possible. So we'll delve into the background of these. And we'll philosophically ask how how much credence do we want to put into it? I want you to be guarded about that. All right, the logic, temperature is supposed to change. That's our working definition, right? 2 times it, CO2 goes up. That was one of the challenges on some of the homeworks today, that the estimate of when it's going to double has to go from the 1950 level, because that was the level to start. We wanted to double it, so it was like 311 or some 310, something like that, so we wanted to go to 320. Most of the time, though, doubling it is fine in the academic sense, but if we're gonna measure the real world, doesn't necessarily double, so we can't just simply measure the temperature, because it's a simplified tool. But if we can get the starting and ending temperature and the CO2 levels, then we can scale it. So I'm going to throw a little algebra at you, how to scale it. We'll set it up with a formula. It should be good to go if we're going to employ it. And so that's the bottom line here. Only in the rare case will see to be exactly 2 times, so we do the scaling business. And algebra is, our nemesis, because it's nasty stuff. The algebra actually looks like this. We're going to call it that climate sensitivity, our working definition. It's the temperature at the end minus the temperature at the start. It's going to be proportional to the CO2 at the end. That should be a minus sign. The CO2 at the start times 2. Okay? So this proportional gets us to the way we go. We're going to introduce another variable just to make the math work. We'll talk about the scaling factor. The scaling factor has to do with the fact it's never exactly 2 times. And so the scaling factor is actually a little tricky in the sense that it's the CO2 concentration at the start divided by the difference, what it is at the end versus what we subtracted. And if this is sort of one of these things where it's a percentage, it's basically a percentage, and percentages sometimes have the difference divided by the amount, right? For 2, it gives us sensitivity of 1 is exactly what we wanted to do. Once we have the C for a particular case, then we can get the climate sensitivity. And it's simply this formula. This number is what we're after for 3 cases. We'll calculate the temperatures at the start and the end. We'll multiply it by our scaling factor derived from there, and everybody will get a good handle on what we want to do. In some senses, this is the slope of the line, and that way you could check the math if you needed to. So far, this is streaming along, and it's all math and theoretical. Questions? The rest of the day is basically not worrying about the algebra, worrying about the events that happened in the history, in the past. Algebra good? It's always good until you try it. I don't know how that works. I developed a spreadsheet to illustrate this. So it's an easy number. For the sake of argument, I have 6 different cases with the temperature at the start and the temperature at the end. It's a 3-degree temperature change. And then I've also taken the CO2 at the start and the end. I get a scaling factor, and then I find out what the climate sensitivity is. So this is our starting point. For this kind of temperature change, we get this kind of CO2 change, double it. This is fairly close to the example you did. So that's a scaling factor of 1, and once we get that, our climate sensitivity comes back out to 3.2. Okay, now, what happens in the case where I have the same temperature change, but the CO2 went up more than double? Okay, how would you describe the climate sensitivity factor? I mean, the numbers there, but describe it.
The numbers go down.
I'm sorry?
They go down.
It went down a little bit. So it went from this to this. Why did it go down? Because there was more it took, in order to get that same temperature rise, I needed more CO2. Okay? Sort of counterintuitive, not necessarily. So I'd like the volunteer, sir, to explain to me this one, please. Yep. What's staying the same, what's changing here, please, in this particular case?
Climate sensitivity is going down, the scale is also going down.
The scaling went down, the climate sensitivity dropped, we've dropped here, and what happened? Why did the numbers change?
Maybe because as a value increases, each individual unit gets less valuable.
That's probably a simpler way to say it, I think. But I had to have more, basically I had to have more CO2 to get to that same temperature change, that 3-degree temperature change, which is just an example. Instead of the 600 parts per million, for 3, and this one I needed more, and guess what? I'm gonna need even more. So when I go from 600 to 900, I have this. Does that mean it's a one-to-one relationship, or is it some kind of screwy number relationship? See, these 4 are all the same example, I just keep ratcheting up the CO2. Right? I just go up 100, 100, 100, something simple. I go up by not doubling it, but these numbers don't go down quite in a linear fashion. There's a little bit of slope to it. Okay, great. Who wants to tackle the negative one? Who wants to tackle? Oh, I'll find it. Yeah. All right, we get a volunteer. But you're on your deck. I got your number.
The CO2 level decreased instead of increasing.
I'm sorry?
The CO2 level decreased instead of increasing.
So what happened? I mean, what does it explain that to me?
So the start of it was 300,
Yeah.
and then it went down to 100 instead of like all the other examples going up.
The CO2 went down, right?
Yes.
And so that gives me a negative climate sensitivity?
Yes, because the temperature's going to be decreasing instead of increasing.
Now, is that physically, that's the math. The math works, right? Is it plausible that that's okay would work?
I do not know.
I mean, here's a mathematical result. When we believe math, right? But is this plausible? It's been drilled into your head, more CO2, more temperature, right? So in this hypothetical argument, you agree that the math is right, but is it physically possible or likely or whatever? How can we assess it? If I could find a real life example, then you'd believe it. We might not know why, but maybe there aren't examples and there aren't examples. So this negative thing is an interesting concept. I don't know of any examples, but I also know that the CO2, part of the challenge here is that CO2 is not the only thing driving temperature change. We're isolating it and putting it on a little pedestal, giving it all the attention. There's far more important things in the climate system than CO2. Water vapor being one of them. So conceivably, I could increase the CO2, but if I messed around with water vapor for some obscure reason, I could end up with a negative temperature, the same temperature change, but with less CO2, giving me this negative number. So the climate system is not only about this. Let's keep that in mind. And then, now, the remaining one, what's the significance, or how would you interpret this particular business? Describe it for me first. Same temperature change, right?
Yeah.
What am I doing with CO2?
CO2 went up.
It's going up. Is it going up compared to the other examples a little bit or not so much?
Not so much.
Not so much. But to get the same temperature change with not so much change, what does it say about the climate sensitivity?
It's high.
Excuse me?
It's higher.
Yeah, it's a lot higher. doubling. So this 300 to 400 it's not a lot, and it changed this number a lot. Again, it's not linear. Is there anybody who has a pressing interest in trying to change some of these numbers and see what they get? It's set up in a spreadsheet that almost works. It sometimes works, doesn't always work. Anybody
Why
has a-
is that one higher?
Why is it higher?
Yeah.
I thought you just explained that to me.
Well, like, I really don't understand it. Like, why is that one higher if the CO2 is lower than some of the other ones?
Because I keep the temperature the same. If I messed around with the temperature, then it's really hard to see the pattern. But I'm always talking about the same 3-degree temperature change. The only thing I'm messing with, I say keep that the same. I mess with this. I could get a whole different set of numbers if I kept these the same and messed with this. It would be so that you would interpret, they would be interpreted a little slightly different. Is it a better explanation?
Yeah.
Okay. Anybody have a pressing need to run a calculation? No? Let's get out of the math. What's this all about? All right, I want to do back calculations, the 3 sensitivities. There are 3 different, very different global warming events. They're going to be different time scales. They're going to be different sizes. So we want to see if the climate sensitivity is or isn't consistent with these 3 natural experiments. The 3 timescales are, I classify them as long, medium, or short. One of them happens over, it happened 55 million years ago, which is not the present configuration of the planet. And it was a fairly large temperature change, and it was a very high CO2 level. The medium is something that happened sort of more 10 or 15,000 years ago at the end of the last ice age. And what we call the Wisconsin glaciation. The temperature change was significant, 5 degrees or something like that. The CO2 was fairly minor change. And then on a very much shorter time scale, something that's basically historic. It's the very end, it's about 250 years ago. Well, now it's closer to 300 years, more than 300 years ago. There was a cool period on the planet's history. As an aside, one of the reasons that we had a lot of discussion about when does the warming start, there was a natural cooling event that lasted for several hundred years, not too long ago. And that cooling event we started coming out of naturally, and then the anthropogenic effect piled on top. So we'll look at something called the Little Ice Age also. And I'm going to walk through a little bit about what's happening for each one of those. You live in an ice age world. It may not seem like an ice age world when temperatures like today, but the configuration of the planet and the climate system allows us to be flip-flopping in and out of the classic ice ages on about a 100,000 year cycle. So you know that, or you should know that. For the last 65 million years, and 65 million years of the time when the dinosaurs went belly up, it's been generally cooling. A period called the Cenozoic. Don't need to get too tied into the names, but geologists like to give names to different time slices. But for the long period of time, it's been cooling in general. It doesn't go constant. There's fits and starts, and we'll see that in more detail, but conceptually. We actually saw a diagram of this, a pretty diagram of the continents. You're going to see that again today. I want to emphasize that CO2 over this long period is changing, but it's really a minor player. There's some other things that are going on, like you move the continents around, that have a bigger deal than the CO2, but nevertheless. In particular, we changed the basic circulation patterns. And this is the theme I'm going to keep coming back to. You change the configuration of the ocean or the atmosphere, or in tandem, and it's usually more in tandem. Then you change the temperature. And this gets back to my nonlinear systems business. So CO2 is a player in there, and again, we're putting it on a pedestal and we're going to focus on it as being the all, get all, be all, but it's not. All right, so the geometry of the oceans and the atmospheric circulations over time during this cooling allowed the poles, which were warm, the polar places. Today we think of as ice cold, it's because they're covered with ice. Well, the southern pole is covered with ice sheets, the northern pole is covered with sea ice, it's the ocean up there. But we started getting glaciation at the poles, and then we got glaciation at lower latitudes. So this is, the cooling is bringing us into this ice age world. The quaternary, so-called quaternary, the last 2.5 million years or so, is where these temperature variations have gotten much larger. Instead of a few degrees coming and going, we've gone to 5 or 6 degrees. And so that's the real ice age cycle. And then the last of those cycles, it just terminated basically yesterday geologically. About 23,000 years ago, the ice sheet was inside the 275 loop of Cincinnati. I think I've said that before. I'll probably say it again because I like that part. That's part of the reason I accepted the job at Cincinnati, because I was interested in studying that particular time slice. But, so that's cold. That's an ice age world. We call those cycles glacial and interglacial, very clever, in between the glaciers. And so the interglacials are the warm times. And by and large, the warm times don't occupy, of the last, during the Quaternary, only about 10% of the time is as warm as today. This ice age world means the climate's been a lot colder for 80 to 90% of the time. Sometimes it's 5 degrees colder, sometimes 4 degrees colder on into the nights. So that's why I contain we live in an ice age world. Because we're at the warm time, and we're gonna try to make it warmer. Think about that for a minute. Here this is graphically. Time is on the deep time, long time ago. Today, there's a lot to decompress with this, but basically they've done two things. You want to follow the red line, basically. And what this is some geochemical signature called oxygen. This one used oxygen isotopes to reconstruct the temperature scale here. And some of you had, you know, the notion of what is the temperature today on the globe is something like 13 or 14 degrees Celsius. And there we are right there, sort of 13 degrees Celsius. And that's the coolest it's been if you go back 65 million years. Okay? CO2 levels up in this part of the time, we don't have a good way to measure them precisely, but they're high, thousands of parts per million, compared to, in essence, an unaltered CO2 level of 250, 300. We quibble over 311 versus 316 and all that. That's because we've been, since the 1950s, we've been able, 1959, we've been able to measure it very precisely. So we get a big deal out of, you know, the difference between 300 and 301. And on this time scale, the notion that we're in the thousands versus a few hundred is the take-home message. The other thing that's on this graph, and I'll come back to each of these individually, are because these are what we call tectonic events, where things are happening because the continents aren't stationary. Over these time scales, they move around. And they banged into each other, and they separated, and then they banged back into each other, different places. But by doing that, I'm going to walk through the details of it, you change the patterns of circulation and things. So here's the global temperature. One of them we're going to look at is the PETM, which is just a really sharp blip right there. The next one we're going to look at would be the last glacial cycle, which basically takes us to here, and then something that doesn't even fall in this, a little ice age. One of the things on here, I need a volunteer. Who's my volunteer? Do you know what hominids are? Hominids?
No.
Anybody know what hominids are?
Humans.
Humans. So where are humans on this thing? Well, Bob, well, they come in late in the game, and they're only about that wide. So this is, humans are in various species, not necessarily Homo sapiens. Homo sapiens is much more recent. Our species way out here someplace, but hominids as a general group came in during sort of the Quaternary. Okay? Anything else on this graph that we should identify or talk about? We'll get you livened up a little bit. You're on tap. You're not going to escape. The graph we saw the other day, this basically has the same information. It's a prettier graph. It puts in some of those contexts in sense. We talked about it the other day. Here's the general long cooling. Here's an approximation of temperature. Here's the deep past. It's not its fancy graph. It's a nice artist representation. But it also has the potential for what's going to happen in the nexus point that's today. And this graph comes out of the punctuated equilibrium paper. But I'll go through a couple of these in general. I just wanted to tie it back to the last lecture. Beginning time, at the beginning of the Cenozoic. The continents were not like they are today. North America had a big ocean up in what is now the Rocky Mountains. A lot of Europe had oceans. India and Asia were not connected. Africa was wet. There was a big gap between North and South America. More importantly, Antarctica and Australia were still connected. There's also a little bit of a connection between South America and Antarctica. So these are the configurations. It's quite a different planet than today. It doesn't happen overnight, but generally, one of the things that did happen was the so-called Asian-Indian collision. India, which was down here but was trucking fast in this direction, ran into Asia and it threw up the Himalayan mountain range and the Tibetan plateau. That's some of the highest topography on the planet. That matters to the air pattern circulation. So this smacking into this did some things. The next one is the formation of what we call the circumantarctic current. They call it circumpolar current. I was making a point a few minutes ago about Antarctica being connected to Australia. You don't have much water going around the Antarctic at that point, but if you separate those two puppies, you can get some circulation patterns. So, sidetracking, what does the modern circulation look like? There's a website that shows us exactly what's going on a minute-by-minute basis. This is the circulation pattern as of this morning on the first part of the globe. And we see that there's kind of windy out here. This is Greenland, Cincinnati's here, Alaska. We're not getting the very southern tip of South America here, but there's the equator. And we see that there's certain circulation patterns. And in particular, there's winds going this way, and there's winds going this way, and that's got a certain name, and we could get into that later. You get some wind patterns here. It's windy here. Here's a storm in the Bering Sea. You know, the ice fisherman is another Bering Sea storm. The details, just to bring this home, this is what zooming in on Cincinnati looks like. The wind patterns this morning were basically to the northwest. They change all the time. My point of this is that the little thunderstorm that inconvenienced us this morning is a blip on the scale. It's not the major thing. It came through, it did a lot of destruction, or not a lot of destruction, but it doesn't show up in changing the circulation pattern. The circulation pattern is bigger than a little old thunderstorm. I mean, that's part of my point. So that's fine. However, those things that really cool around are a big deal. So here's a view from directly over the South Pole, which would be right there. Here's the Antarctic continent. In this diagram, Australia is here, separated by something like 1,800 kilometers. And then there's the Drake Passage, which goes from the Antarctic Peninsula to the southern tip of South America. and that's 1,200 or 1,500 kilometers. And what happens? We get big storms. Look at these puppies. Red's not good if you want to be a sailor. But these puppies, these are the atmospheric thing, rotate around. And we'll come back, next, if I brought one of these up Tuesday, you'll see these storms have changed positions. Why? There's nothing there to stop it. This is all open ocean. Because Antarctica and Australia is separated. So we've got this real belt of places where the ocean could run free and the atmosphere runs free. And I'm kind of partial. I've spent a fair bit of time down in this part of South America, and so we get nailed with the wind quite frequently. So I know what these look like on the ground. All right, the last event, this long Cenozoic cooling, is this fact that we started reconnected South and North America. And that, before, it was a hole, but this area rose up, and so we connected Mexico and through Panama to South America. Now, it's not a very big connection, but it stops ocean circulation. And if we go to our handy dandy, this is the same website, but I'm showing the ocean circulation now. And so the white bands are ocean circulation patterns. There you, sir. Yeah, what's your name?
Adam.
Adam? So the white bands of ocean circulation, do you see any patterns there that you've seen before anywhere? Or not? I'm just curious. So you recognize where we are. This is North America, Florida, Cincinnati. Doesn't matter how far down there, California. This is the water in the ocean, right?
It's the same ones as the ones we just saw.
They're
similar.
They're a little bit different. Do you suppose that they are they change as frequently or less frequently?
Probably less.
The ocean changes a lot less than the atmosphere. The atmosphere, 24 hours, the atmosphere will change a fair bit. The ocean, not so much. So this is what's called the Gulf Stream, if you haven't never heard of it. It's a warm belt that originates in the lower latitudes. The equator's here, so it's really hot. And the water comes floating, zipping in here, gets warm and toasty and makes a loop, and then it comes back out and takes warm water up into the North Atlantic. This is going to be involved with something called AMOC. It's going to be a primary, one of the lesson modules. And if I brought up the exact configuration of it, in 3 or 4 weeks when we do it, you'd see different squiggles with here. But the point is that those patterns are the same. What I draw your attention to, for the sake of argument, look at these currents right here that are just not quite at the equator. There's a lot of water flow there. But we don't have a connection between the Pacific and the Atlantic Ocean today. So all of this current here, at a time in the past, would have interfaced with the ocean. And one of the more important things that happened at that time was it bring the salinity changes. This is hot and a lot of evaporation going, and it gets salty. This would have given it fresh water, but we've cut off the fresh water. So we'll see how the salinity changes circulation in a bit. So bottom line of the last 4 or 5 slides, you change the continent configuration, you're going to change the fundamental circulation patterns, for better or worse. That changes temperature. Now, going and focusing on the PTM event, which is 55.5 million years ago, or was. It's also P, KLSE, Eocene, those are fancy geologic names, thermal maximum, hot time. The ocean currents had to be quite a bit different for reasons I just talked about. The planet was too hot to support the ice sheets. There were glaciers at high elevations, but there was not ice masses at the southern pole or the northern pole. This evidence for this is all isotopic, geochemical mumbo jumbo. And it's a little bit contentious because it's so fast geologically. We're going to talk about 200,000 years, which seems like a long time, but 55 million years ago, that's actually hard to resolve. This is a fifth of a million years. And so something that's this far back, there's some issue. So this is the reason that there's some debate about the evidence. And we are intrigued by why these events would happen. Now, there's nobody, I don't think, that would argue that changes in the CO2 level forced the warm event. I don't think there's anybody, I could be corrected, but I don't think there's anybody who would argue that this warm event was caused by changes in the CO2 level. But there's a lot of people who have observed and argued and documented that the warm level was associated with this change in the CO2 levels. And so if there's a temperature change and a CO2 change, we can change climate sensitivity. It's probably one of these things where it comes in and it has a role to play, but it's not the big dog. All right, so this is the PETM. This is one event you're going to love to research. And what else do we need to know about the PETM? We're going to look at it a little bit more detail. I've taken, it's a slightly different graph. It's a little more technical graph, but here's an approximation of temperature. And there's two things that are kind of weird here. One is this pulse here. You see, it's not perfectly by itself. It's not just this is the 55 millimeter PETM event. This one we don't care about, of course, because it's a global cooling event. Now, why would you'll see in the Oligocene boundary, that's actually one of those changes in the configuration of the oceans. So here's the thing that we want to do that. The oxygen is there. Everybody, well, there's various ways to measure the carbon. There's a question, how did you get it in the atmosphere so fast? There's nobody riding automobiles around right now. And the amount that we're putting in the automobiles in the atmosphere is nothing compared to these things. All right, so that's a PETM. Let's see. Red shirt, please. What do you need to know about anything about the PETM to satisfy any questions, pressing questions?
I wrote down that it was prior to ice sheets. Does that mean that ice sheets didn't exist before then?
They actually came quite a bit later. It does, you're correct. Let me jump back here. And this graph, so the PETM's out here 55 million years ago. As we move this way, you see this is talking about the Antarctic ice sheet. This is schematic, but there wasn't any Antarctic ice sheet until sort of 40 million years ago. Then it got bigger, then it got big, then it got small, then it got big. So here's the southern hemisphere ice sheets coming. The northern hemispheres did the same trick, but much later. You don't get the northern hemisphere's ice sheets until 10 million years ago. So this is symbolic of it just gets cooler. Well, you have a continent around the pole, that's where you're going to build an ice sheet first. The one that came to Cincinnati out here, we're a long ways from the pole. So that's the symbolic of the cooling. Does that help?
Yeah.
Anything else on the PETM before we move on? All right, we're off to the looking at, yes, sir.
Yeah, could you please the last part, the last PowerPoint,
I'm sorry?
the last PowerPoint, the PETM one.
Yeah.
So, does it mean 40, like before 40 minutes here, there's no ice sheet in this graphic?
That there were no ice sheets?
Yeah.
Yeah, this is what this is the southern hemisphere ice sheet.
Ice sheet, when the ice sheet starts, right?
When they
I mean,
start,
that point.
more or less. I mean, approximately 40 million years ago, yes. The northern hemisphere, there were tropical plants up in Greenland today with an ice sheet until in here someplace. Alligators, tropical plants, rhinoceroses, and that kind of thing. Up as far north as we have land today. Okay? Good question. Now we're going to go into the Ice Age cycles. I could bore you to tears about it because this is a subject near and dear to my heart. We're going to look at the last sort of million years, 800,000 years. We're actually just looking at a teeny piece of the chart. Because we're down in the last million years, hominids have shown up. Homo sapiens can be in here someplace-ish. And the general point is that this is CO2. And they've identified sort of an average, just for chuckles, but there's low values of CO2, 190, and there's higher values, about 280-ish. And what you see in the CO2 levels, they keep bouncing back and forth. Not in exactly a systematic way, but they're up, down, up, down, up, down. And it's 100 parts per million. Percentage-wise, going from 190 to 300 is a big deal, from 200 to 300 is a big deal, but it's only 100 parts per million. And these are tracking the coming and going of the northern hemisphere ice sheets. If we zip back to this slide, the red is the average, and things bounce around on top of the red. And they bounce around, and sometimes they bounce a little bit, and sometimes, well, this is a little bit, this is medium. Other times they bounce like a yo-yo. We've come into the yo-yo times, which are the ice age cycles. And here's one blown up, just that little itty bitty part of it. And it's bouncing around like a yo-yo. These are associated with the cold. The low CO2s are cold. The high CO2s are associated with, I'm not going to say they caused, are associated with the present day warmth. And the point is that if you pick some number, like for the last 100,000 years, it was warm and then cold, and then today it's been warm for sort of 12,000 years. And that's the warm we're living in. Now, academically, I could say, well, let's plot the CO2 levels today on this graph. 311 was 1950. So 1950 was already sort of higher than it's been in the last 100,000 years. You see that hyped in the press all the time. But 1950 was not so much. What's today's value? 420 what? I don't know. 420s though, right? So if we put 420 on here, we're up here someplace. So this is where you get to the point that the CO2, the arguments that the CO2 is higher now than it's been in millions of years. And you'll see different papers will talk about different amounts, but it's real. This is not to say that the ice age cycles are driven by CO2. For the ice age cycles, they're a tracer gas. They come and go into the oceans, and they bounce around this much. They add some, but they're a really minor player. This has to do with amount of energy coming in from the sun drives this. We're at a point where the sun energy can change a little bit, and lo and behold, you get an ice age or not. Catastrophically, I might add. So we want to look at this last catastrophic. Here's the time spruce trees are growing in Cincinnati, and then all of a sudden we kick out of that ice age. Boy, there's a good sort of, not 100 parts per million CO2 change, but it's significant CO2 change, and then we could figure out how much temperature change it is. It's going to be on the order of 5 degrees, and we can calculate a sensitivity. So I'm just telling you it's 5 degrees, so you don't get something that comes up like 27 or something. It's not exactly 5 degrees. Zooming in even closer on that scale, again, logarithmically, here's what the temperature looks like for the last 100,000 years. This is the last, not the current. This was the last interglacial. It was sort of as warm as today. It got cooler. We can debate the pattern of this. Cincinnati, right here, bang, the ice sheet was as big as they're ever going to get. And then it got warm. A way to calculate, we know the temperatures, and we can calculate the climate sensitivity. Okay? We'll be revisiting this specific warming event in the last module of the term. The third example for the homework is this little blip in here. See, this is the warm period, but within the warm period there's blips. Climate's changing all the time. And we want to look at the sort of the last, well, on this graph it's about the size of that dot. Okay? So that's something called the Wisconsin or stage 2 glacial part of the ice. So zooming in again on that little blip to look at temperature changes, we see this is year AD. So here's the year 2000 you're used to. We're out here at 2020. I guess we're here at 2020. And we've got warm temperatures, and this is 1950s about here. There's an interesting stable period of time during the 1940s, and then there's a cold time, cold about 1 degree Celsius, that persisted for several hundred years back to, you know, AD 400, 600. We fight incessantly about when it started, and that bores everybody to tears that's listening. But there is a colder period there for, call it 300 or 400 years. We will find some people pick a period in here as the cold time, and we'll get the temperature CO2 levels. I would not go younger than 1940 for this exercise. I would call 1940 the end point of the warming, because this is the natural warming. Parts of this are anthropogenic. So let's not mix them up. I mean, let's keep them divided so that there's less reason. So call it 1940 as a decent time to end the exercise. So what happened during the Little Ice Age? It started warming naturally for whatever reason. Stalled, and then it's taken off because of anthropogenic was in-ground. It's the warm time, the cause is up. Is little, you've probably heard of the Irish potato famine. That's one of these times in here where it's cold. Part of the reason is they had a famine was because conditions didn't permit growing potatoes in Ireland. Happens on one of those little lots. I don't remember which one. Okay. Where are we at now? You ready for, what do we need to know about the Little Ice Age? Let's go back. We did this for the PETM, but we didn't do this for the, oh, these are my glasses. Let's do this for the Ice Age world. Let's go back to the gentleman in the gray shirt. Yep, good call. What do you need to know about the glacial cycle, the 100,000-year-old pulse speed? What more do you need to know in order to make sure that we're on base to calculate the climate sensitivity?
I guess just like how it affects the wind cycles and how that changes the CO2 levels.
All right, so you've asked a very complicated question. The wind cycle patterns, basically, we have what we call we haven't talked about it yet, there's something called the westerly circulation belt. I don't know if you've ever heard of Hadley cells or not. There's a pattern to how the atmosphere, where the winds come. In our latitude, the winds come from the west primarily, for reasons we will go into, but not for depth today. That belt, and it's a few degrees of latitude, so it covers from say here up into a third of the way up to Canada, and it doesn't go much further south than the Gulf states, basically. But anyway, that belt of westerly winds, so there's one in either hemisphere, change in and out of the ice age cycle. They don't change much. So if we go back to this, in the southern hemisphere, the westerlies are sort of in this part of Chile today. This gets hammered with high winds, but the westerly belts are here. In the ice, at certain times, under certain conditions, though, the position of those migrate up and down. They migrate, say, from here to Georgia. And so that's a change in the atmospheric circulation pattern that does make a difference for the globe. There's a chicken and egg question, whether it's because the globe's warmer that they do it, or because they do it and that makes the globe warmer. But they do change. That was the first part of your question, right? And the second part, would you mind, please?
Just how that affects the CO2 levels.
Now you've gotten into a really nasty question. Turns out a lot of this big ocean out here called the Pacific. There's upwelling and there's places where the water comes up from the deep ocean to the top, and there's places where it goes down. When we talk about AMOC, we'll get into this deeper. But basically, the ocean is the final repository of CO2. It'll all absorb back into CO2 if we didn't do anything. During the glacial cycles, that 100 part per million thing is a modulation of the ability, the net ability to absorb or spit that stuff out by the oceans. So that's how it's associated with it. Again, the 100 parts is not enough energy to drive the temperature changes that we see, but that's part of the enigma of the CO2 sensitivity. Is that making sense or not? Did I jump into that too deep? Okay, anybody else for the gentleman in the black shirt, please? Question that you have about ice age cycles.
I guess sort of to expand on that, would an ice age cause there to be like less CO2 absorption because there's less ocean? Or
The ocean levels change because the ice piles up on the land, and it changes 120 meters, but in the grand scheme of things, there's not much ocean. But the CO2 levels, so it doesn't really change necessarily the amount of ocean for the CO2 to go in. I think that's what you were asking, right? Yeah, that's minor. That's a lot of surface area right there. If we took and dropped sea level 120 meters, there's places where you could see a difference on the map, and there's a lot of places you couldn't. Did I get to your question? Okay, the lady way in the corner. What do you need to know about ice age cycles that you never thought about until just recently?
I'm not really sure. I don't know.
But can you explain them to me? You comfortable explaining them to me? Well, then there's got to be a question. How long are they, roughly? The ice age cycles. They come and go like a yo-yo. This is yo-yo time. How fast? As fast as I can. Well, I can't make a yo-yo work anyway. But 10 years, 1,000 years, 10,000 years, 100,000 years, millions of years?
Yeah, I'm not sure.
I'm having a little bit of problem hearing you, so I'm going to ask you to speak up a little bit, but let's bring up a graph and see if this helps us a little bit. So here's the pattern of the yo-yo. This is 800,000 years. How many yo-yo events do we have here? 1, 2, 3-ish, 4-ish, 5-ish, 6-ish, 7-ish, 8-ish, 8-ish, and 9-ish. So roughly how long are they? About 100,000. 100,000 is the number we use for okay? How much CO2 is associated with differences? It's on the left-hand side. Is a lot of CO2 or not so much?
Not so much.
Not so much. I mean, it goes down to 190. There's a change in the size of these things about 400,000 years ago. See, the yo-yos weren't quite so fun and games back then. But today, it only goes up to 270, 280-ish, something like that. A little less than 100 parts per million, around that. Okay? So we pick out one of those cycles for the sake of our homework. and I'd pick out the last one, and there's the warm time, and there's the cold time, and we need to figure out how much CO2 exactly it is. It's gonna be on the order of 100 some odd change of CO2, parts per million. Okay? But you've got your time slice. Are you gonna divide that or use 100,000 years, or are you gonna use something else for the change? There's 190, there's 270, right? So here's the CO2 graph. That's the 190 and that's the 270-ish. So how long a period of time? We talk about the yo-yos being 100,000 years, but how fast, or how long did it take for that CO2 to go up? I would argue it goes from here, whatever this number is, you can't read it necessarily, to here. That's where the temperature jumped. And that's when the CO2 changed. And in round numbers, it's gonna be something on the order of 10,000 years, not the full 100,000. The rest of it's out here someplace. Okay, does that clarify what ice age cycles are and how specifically, so you're gonna find different numbers than 10,000, but they're gonna be in the ballpark of 10,000. So don't try to use 10 years or 1,000. It's order of magnitude, most of this stuff, folks. Okay, so we need any more on the ice age? Let's go to the little ice age. Who wants to jump into the little ice age? Lady in orange, tank top there? I don't know what color it really is. This one's historic, man. This is like, you know, the rise and fall of different. There's civilizations that came and went. You know, here's the Romans are back in here and stuff. Medieval dark period, the Dark Ages, and European civilization. It's all history, man. Right? Just a second.
Just what?
Oh, the gentleman behind you wanted to raise, but I want your question first.
I guess like how did like the CO2 levels like affect those like historic like groups?
So this is the question of how much is the CO2 levels really happening, right? And so this particular graph has this whole kit caboodle doing something on the order of a half a degree C. This is baby compared to the other ones we had. But this is the one where we've tried to raise Western civilizations and, well, the Eastern civilizations were going back a lot further than that. I mean, reality, people are building cities back in here someplace. Okay, but back to your question, how much CO2 is associated with this half degree? Not gonna be much. To get this thing, we're only talking 100 parts per million, right? So to get this, we've got to be looking at some fraction of that. So let's look for tens or fives or something like that rather than 500. That bring it a little home. Anything else you want to know about the little ice age? That's good. Sort of a half a degree temperature change depends when you pick it. And as I said, don't go any younger than 1940. You got to pick points, and people pick different points, but 40 is a good, 1940 is a good endpoint. Yes, sir.
Why is there lots of debate about the cause of the little ice age?
Why is what?
Why is there lots of debate about the cause of the little ice age?
Well, because it doesn't fit any of our preconceived ideas. There's no fundamental reason for it to happen except that it did. So there has to be some fundamental reason that we don't understand. And the group that I work with refuses to talk about it because we don't understand it. So this is cold times, that's no problem, warm times. But what you get is in any graph that you have of the last 10,000 years, there's wiggles at different scales. And this is, the little ice age is the last of that wiggles. The explanations range everything from the fact that the sun can modulate things to the fact that the sun output, like solar cycles, are often attributed. There's also an argument about the insulation, that the Earth and the sun aren't the same distance all the time. And so there's an insulation argument, this longer time slice that explains this. But and if you calculate in the future, we are losing on that particular property, the insulation factor. The other things have to do with wobbles. Other things are more related to no, I went too far now. Wobbles. This is a fluid. One of the properties of fluids is it snakes back and forth, right? And little parts of the cells become chopped off. If we go back in geologic history, this warm current, which ends up on the other side of Iceland nowadays, during the Ice Age went down, went straight across the ocean to Portugal. So that changed a lot of energy balance. So there's some that would argue that this dipping part way could give us the Little Ice Age. So there's a couple different mechanisms out there, and actually we debate them. Go ahead.
Do you think it could be like all those factors combined, or just like primarily just like one of those, like the Earth?
Yeah, speak up, please.
Do you think it could be like all those factors combined that cause that, or just like one main one?
Oh, if I had to guess, I would say it has to do with the ocean.
Okay.
Not a complete ocean change, but a blip in the ocean. The time scale's about right. That's me personally. I mean, I've studied the Little Ice Age in New Zealand and Alaska and other places, but I'm getting very confused by it. We've gone through the time slices. We've gone through all of that. We need to get out of here. It's getting late. Exercise. 3 time slices. Dig into them a little bit. Basically, you need to give me where you got the CO2 levels and the temperature change. Set up the formula. Calculate them. I've already told you they're not going to agree. Wow, that's boring. Why? The why. This is the head scratching thing. I'm not going to judge you or evaluate you on the correctness of the answer. I'm going to evaluate whether it's got a reasonable argument, whether you make an argument. It is because it isn't going to get you much. It is because the continent shifted, and specifically we ran India into the Himalayas. Would. I'm not saying that's an answer. I'm saying something on that order is an answer. Be sure to give me all references so we can double check. They'll be the same characters. And that's a bonus, that's a give me bonus question. Now that we've really gotten into these things, or dug a little deeper, we're going to be a little more philosophical next Tuesday about, well, why is it important? What does it really mean to us? Okay? Anything else? Ma'am?
When we go to calculate the climate sensitivity, are we supposed to start like from the very beginning of like all the graphs, or do you want us to pick like one peak in between?
I'm not following.
Like for the CO2 start and the
Mhm.
temperature start, like.
That's sort of a subjective thing, but we talked about that a little bit here. This is where it's really changing, so we want to start here and end here, right? Whatever, you'll find those numbers on a better graph, but don't talk about the CO2 from here to here. That's going to give you a very different sensitivity, isn't it? And it should be the same. I don't know. Well, it should be the same number, but it can't be quite the same number because it changes. So you'll have to find a specific time in order to stick it in the formula.
Just like any time.
Well, no, you got to justify it. But it will go into the formula here, right? time end minus the time start, so how long did it take? And in round numbers, we're talking at tens of thousands of years for the PETM, we're talking 10,000 years for the glacial cycles, and we're talking of several decades for the for the Little Ice Age. So be a little more specific than that, but that's the right order of magnitude. Okay? Anything else? Have a good weekend. I'll see you on Tuesday.